students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as oscillation. Now, we had seen what is SHM. Let us see SHM as a projection of UCM. Of UCM on any diameter. Let's assume that you have a body, you have a circle. Consider particle P performing SHM on the circumference of the circle where AB is the diameter. Let's consider that AB is the diameter and a particle P is performing SHM on this, right? So consider a particle P performing UCM along the circumference of a circle with AB as the diameter. So I'm going to have a particle P that is going to perform UCM here, right? Now, let us assume that let M be the particle which always remains at the foot of the perpendicular drawn on AB. I'll draw that and show to you, just give me a minute. Let M be the particle which always remains at the foot of the perpendicular drawn on diameter AB. From the position of particle P. Now let us take four different positions of particle P. Let us consider that the first position of particle P is P1. We said that M is the foot of the perpendicular, so from particle P, if I drop a perpendicular on diameter, that will be my M1, right? Let us assume another position of particle, say let's call this position as say P2. Draw a perpendicular. This is going to be M2, which is going to be my foot of the perpendicular. This is my second diameter, right? O is the center. Let's draw another position. Let's call this position as say P3. Let's call this position as P3. Drop a perpendicular here. If I drop a perpendicular here, then this will be M3. And similarly, let's call this point as say P4. So if I drop a perpendicular here, this will be M4. So M1, M2, M3 and M4 are the foot of the perpendiculars for point P1, P2, P3 and P4. Fine, do we get this thing clear? Right? So that is what I had said. Particle P is performing UCM and along the diameter, along a circle whose diameter is AB and M is a particle which is the foot of the perpendicular of point P. Fine, do we get this in here? So you'll say let point P have successive positions P1, P2, P3 and P4, right? And along the circumference and particle M have positions M1, M2, M3 and M4 along the diameter. Right? Right. Now once we have this, thus I can say that particle P maintains its UCM on the circle and particle M continues to move to and fro along the diameter. I can say as particle P maintains its UCM along the circumference particle M continues its motion of to and fro between endpoints A and B. Particle M continues its to and fro along the diameter. Continues its to and fro along the diameter between points A and B. Right? Now, what does this move? What does this prove? This proves that as a body does UCM, if I take the projection of that point, if I take the projection of that particle doing UCM, I will get a motion which will be nothing but SHM. If I take projection of point P along the diameter, what we see is that particle M moves to and fro along the diameter, which is nothing but SHM. Any motion which is made up of to and fro is nothing but SHM. Right? We can write this down. We can say that let's mathematically prove this. Here I can therefore say that as particle P performs UCM, its projection on diameter M, particle M performs SHM. Right? Now I'm going to mathematically prove this to you. Let's see this. How a UCM has its projection as SHM. This is your diameter AB, center O, so we draw another diameter here. Right? Now let us consider that initially the particle is at position P0. Right? And it is covering an angle of alpha with the vertical. That means let us assume that angle DOP0 is alpha. Right? Let us assume that the particle moves from P0 to point P. Let us assume that the particle moves from P0 to point P such that angle P0OP is nothing but omega t. Let's assume that the value of this angle is omega t. Let's assume that M is the projection of point P. M is your foot of the perpendicular, right? Let's assume that M is the foot of the perpendicular and let the radius of the UCM be A and the distance covered by the particle along the diameter be x, right? And this distance is covered along the diameter in time t. So let's just write this much down. We'll say let a particle start from point P0. Particle start from point P0 such that angle DOP0 is alpha, right? Now let the particle arrive at point P. Let the particle arrive at point P in time t such that angle PO P0 OP is nothing but omega t, right? Let m is the particle which is at the foot of the perpendicular drawn from any position of the particle in UCM along the diameter. So we've written all our initial assumptions. I can say that let us also assume that in time t, particle m has covered a distance of x from mean position O. In time t, particle m has covered a distance of x from mean position O. Right? In which case I can therefore say that in triangle OPM, guys, can you see the figure? In triangle OPM, it's a right angle triangle. I can therefore say that OP, I can say that OM is equal to OM. Now if this angle is omega t, then in that case I can say that angle, or I can say that sine of angle MPO, sine is nothing but opposite is OM upon hypo, which is OP. Therefore I can say that OM is going to be nothing but OP into sine of angle MPO, right? Can you just see the figure once again, please? Right? Now I can say that angle DOP will be equal to angle OPM, alternate angles. Guys, see this. Angle DOP will be equal to angle OPM, alternate angles. Now angle DOP is alpha plus omega t. That means angle OPM should also be equal to alpha plus omega t. That means I can say that OM is equal to OP sine alpha plus omega t. Right? Now let us assume that V be the velocity of particle m. Right? Now what was OM? OM was nothing but x, the displacement. Right? I can say velocity by definition is nothing but rate of change of displacement. Velocity by definition is rate of change of displacement. That means d by dt of x. X is nothing but OM, and OM we had found out as OP sine alpha plus omega t. Length OP we have assumed as A, right? D by dx of sine u is nothing but cos u alpha plus omega t. D by dt of alpha plus omega t. This is nothing but A cos alpha plus omega t. D by dt of alpha is 0. D by dt of omega t will be nothing but omega. So this is going to be nothing but A omega cos omega t plus alpha. In that case, if this is the velocity, if let capital A be the acceleration. If I consider capital A to be the acceleration, acceleration is nothing but the rate of change of velocity, right? We've just found out the velocity, so I can therefore say that acceleration is d by dt of a omega cos alpha plus omega t. A omega as it is, d by dt of cos u. Cos u is minus sin u du by dx, so d by dt of alpha plus omega t. So in that case, that's minus a omega sin alpha plus omega t. Alpha is 0, this is going to be nothing but omega square, because d by dt of omega t is going to give you omega, right? Now this can be written as minus omega square into a sin alpha plus omega t, but a sin alpha plus omega t is nothing but x, which is equal to minus omega square x. So acceleration is minus omega square x, but a is equal to minus omega square x is the expression for acceleration of a body in SHM, right? How do I know this? Because from the expression it is very clear that the acceleration is because from the expression it is very clear that first acceleration is directly proportional to displacement, right? And the negative sign indicates that a and x are in opposite direction. Thus, we have mathematically proved that the projection of a UCM along a diameter is nothing but SHM. Thus, it can be concluded that the projection of a particle in UCM along the diameter is SHM. Right? That's how you prove that projection of a particle in UCM along a diameter is SHM. Next, let's see the second thing. Right? Let's see the second thing. What do we understand by a phase of SHM? What do we understand by phase of SHM? Now, before I explain to you what is phase of SHM, let me first explain to you what is amplitude. Now, let's assume that a body is moving along SHM. This is the mean position. This is my positive extreme. This is my negative extreme. The maximum distance that a body would cover from the mean position would be called as its amplitude. The maximum distance that a body would cover from its mean position on either sides. The maximum distance that a body would cover from its mean position on either sides is called as the amplitude of SHM. Thus, I can say that amplitude how do I define amplitude? Amplitude is defined as the maximum displacement of a body or of a particle in SHM from its mean position on either side. Mean position on either sides. So the maximum displacement of a particle in SHM from its mean position on either sides is called as amplitude, right? Next, let us try to understand what is period of SHM. Right? Now, first of all, let's define what is period of SHM. Period of SHM is the time taken by SHM to complete one oscillation. Right? How do I define one oscillation? A particle executing SHM performs the same set of movements again and again. One such set of movement is called as oscillation. That means, suppose if this is my mean position, this is my positive extreme, this is my negative extreme. A particle starts from mean position, goes to the positive extreme, from there goes to the negative extreme, and then comes back to the mean position, and that set of movement will be called as one oscillation. And the time period taken for that oscillation is called as the time period of the body in SHM. So, first of all, what do you mean by oscillation? How do I define oscillation? A particle executing SHM, a particle executing SHM, a particle executing SHM performs the same set of movements again and again. One such set of movement is called as an oscillation. Is called oscillation. Once I know what is oscillation, then I can define period of SHM. How do I define period of SHM? It is the time taken by a particle in SHM. It is the time taken by a particle in SHM. It is the time taken by a particle in SHM to complete one oscillation. Fine, that's how I define time period. Now let's derive an expression for time period of a particle in SHM. Now I can say that for an SHM, I can say that displacement is equal to A sine omega t plus alpha. That is the expression for displacement of a particle performing SHM, right? Now, after a time interval of 2 pi by omega, after a time interval of 2 pi by omega, let us assume that the displacement is x bar. Let displacement be x bar. Right? In that case, how will I get the expression for x bar? X bar will be equal to A sine omega. We have said that after time interval of 2 pi by omega, that means now my time interval will be 2 pi by omega plus t. I already had displacement at time interval t. Now I am moving ahead in time by 2 pi by omega. So now my time interval will be t plus 2 pi by omega plus alpha. So after a time interval of 2 pi by omega, my displacement is going to be A sine omega t plus 2 pi by omega plus alpha. This can be written as A sine omega t plus 2 pi plus alpha. If I open the bracket, omega would get cancelled. This can be written as a sine 2 pi plus omega t plus alpha, right? Sine 2 pi plus theta, first quadrant, allied angles. First quadrant, sine ratio is positive. Since it is 2 pi, the trigo ratio remains as it is. So this will be sine omega t plus alpha. So if I use allied angles, I will get this that x bar is going to be equal to a sine omega t plus alpha, which is nothing but x. A sine omega t plus alpha was x. Thus, I can say since x bar is equal to x after a time interval of 2 pi by omega, therefore I can say that thus the particle is in the same original condition, x after a time of 2 pi by omega. That means after this much time the particle will be in same original condition. Therefore I can say that the particle completes one oscillation in a time interval of 2 pi by omega. Therefore the particle completes one oscillation in 2 pi by omega time. It completes one oscillation in a time of 2 pi by omega. Therefore, I can say that time period for a particle in SHM is nothing but 2 pi by omega. But when we had derived a linear equation, a differential equation of SHM, we had said that omega square is nothing but k upon m. In the derivation of the differential equation of SHM, we had said that omega square is nothing but k upon m, where I had said that omega square is nothing but force per unit displacement upon mass. Force per unit displacement upon mass. Right? Now, force per unit displacement upon mass. Now guys, just let's mentally do this. F is equal to ma. Therefore, I can say F upon m is going to be equal to a. Here I have F, I have m here. That means I should get a. That means I can say that omega square is nothing but acceleration. Why acceleration? Because this is force upon mass. Per unit displacement, so omega square is going to be this. Thus, I can say that omega is square root of acceleration per unit displacement right? I now know the value of omega, but t is equal to 2 pi by omega. You just derive this also, that time period is 2 pi by omega. Hence I can say that t is equal to 2 pi upon omega. Omega is acceleration per unit displacement, square root of acceleration per unit displacement, right? So that is the expression for time period of a particle performing SHM, right? Hence I can say that the expressions for T are: T is equal to 2 pi by omega. T is also equal to 2 pi upon root of k by m. T is also equal to 2 pi root of m upon k. and T is also equal to 2 pi root of mass upon force per unit displacement. Right? Those are the different expressions that you can have for time period of a particle performing SHM. Next. Next, let's find out the frequency of a particle in SHM. Frequency of a particle in SHM, right? Now, how do I define frequency? Frequency is defined as the number of oscillations per unit time, right? So, frequency is definition-wise. Definition. How do I define frequency? It is the number of oscillations. It is the number of oscillations performed per unit time. It is the number of oscillations performed per unit time by a particle in SHM. Right? Once I have this, now I can therefore say that frequency is nothing but 1 upon time. Right? But we have already said that T is equal to 2 pi by omega, therefore frequency will be omega upon 2 pi. Right? Thus, I can say that n is equal to omega. Omega is nothing but acceleration per unit displacement. We have derived that omega is acceleration per unit displacement, square root. Omega is acceleration per unit displacement upon 2 pi, right? Thus, frequency of a particle performing SHM is nothing but square root of acceleration per unit displacement upon 2 pi, or it could also be written as n is 1 upon 2 pi. Acceleration per unit displacement is nothing but k upon m, so square root of k upon m. Right, that is the expression for frequency of a particle performing SHM. Finally, let's move on to what is phase. What do we understand by phase of SHM? Now, how do I define phase? It is a quantity which completely describes the state of oscillation of a particle in SHM. At what angular position it is. Remember, I had told you that SHM is nothing but the projection of UCM on a diameter. Now, if a particle has moved through an angle, say this is omega t plus alpha, right? In that case, how much distance it has covered along the diameter, right? So, the angular distance or the angular displacement of a body is called as your phase of SHM. So when I talk about phase of SHM, it is this angle alpha by which the body has moved. Right? The quantity alpha completely describes the movement of a body in SHM. It completely describes the state of oscillation of a particle in SHM, and that is called as your phase of SHM. Fine, do we get this thing here? I can say that the quantity, definition wise, the quantity which completely describes the state of oscillation which completely describes the state of oscillation of a particle in SHM is called as phase of SHM. In simple language, for your understanding, that angle, the angle that comes after sine omega t plus alpha is the phase of SHM. The angle that is described by a body in SHM is called as the phase of SHM. Omega t plus alpha is the phase of SHM. Right? Now here, the angle alpha is called as the initial phase. Alpha is called the initial phase. Right? Some authors also refer to this as phase constant or epoch of SHM. Initial phase, phase constant or epoch of SHM. Right? That's how I define phase of SHM. Right? Now, let us try to find out the minimum and maximum velocity of a particle in SHM. Minimum and maximum velocity of a particle in SHM. Now, velocity of a particle in SHM, we've already derived this expression. I can say that velocity v of a particle in SHM, we derive the expression velocity is nothing but omega square root of a square minus x square. Right? Now, let's consider the various alternatives. When the particle is in mean position, case 1. When particle is in mean position. If particle is in mean position, then the displacement of the particle is going to be 0. It has not started moving as yet. In that case, V will be nothing but omega square root of a square minus 0. Right? So in that case, I will get V is equal to nothing but a omega V is going to be equal to a omega square root of a square is a, right? So this is going to be the maximum velocity of a particle in mean position, right? Thus, I can say that V max is a omega. That is going to be the maximum velocity of a particle in mean position. Now, you would say, sir, how do you know that this is the maximum velocity? Or you know this could be minimum or this could be intermediate velocity. I'll prove this to you with case 2. Consider when the particle is in extreme position. If the particle is in extreme position, then the displacement of the particle will be equal to the amplitude of the particle. If the particle is in extreme position, then the displacement of the particle will be equal to the amplitude of the particle, in which case I can say that velocity is given by the formula omega square root of a square minus x square. V will be equal to omega square root of a square minus a square. V will be equal to 0. That means the velocity of the particle at both the extremes will be 0. Hence, the particle at extreme position has minimum velocity. Its velocity goes on increasing, becomes maximum at mean position, and then decreases back towards the other extreme. Fine. Therefore, I can say that the minimum velocity is 0. The minimum velocity of a body in SHM is in extreme position, and the maximum velocity of the particle in SHM is in mean position. Fine, do we get this thing clear? Let us also try to find out the minimum and maximum acceleration. Minimum and maximum acceleration of a particle in SHM. Right? Now again we have already derived expression for a acceleration of a particle in SHM. I can say that acceleration A of a particle in SHM is given by the formula A is minus omega square x. We have done this derivation that the acceleration of a particle in SHM is minus omega square x. Now let us try to find out what is the minimum and maximum acceleration. Case 1, when the body is in mean position. When the body is in mean position, the displacement of the body is going to be 0. In mean position, the body has not yet started moving, so the displacement of the body is going to be equal to 0, in which case I can therefore say that acceleration will be equal to 0, because minus omega square into 0 will give you 0. Hence, in mean position, the acceleration of the body is going to be equal to 0, right? Since it is 0, we will call this as A min. Minimum acceleration of the body is in mean position. Right? Do we get this thing clear? Now, case 2. When the body is in extreme position. When the body is in extreme position, then I can say displacement of the body will be equal to the amplitude. In extreme position, displacement of the body will be equal to the amplitude. So in which case I can say acceleration is minus omega square x can be written as A. So therefore this is going to be my maximum acceleration. Maximum acceleration will be minus omega square A. A max is going to be minus omega square A. So the maximum acceleration of the body is in extreme position and the minimum acceleration of the body is in mean position. The maximum acceleration is minus omega square A and the minimum acceleration is 0. Fine, do we understand this? So do we understand the minimum and maximum values of velocity and acceleration? Right? Okay, we will stop this here for the day. Thank you very much.